And before we get to Rolle's theorem, before we get to the mean value theorem, we first look at a special case of the mean value theorem. And this special case is called Rolle's theorem. Now, in the intermediate value theorem, you had two conditions that were satisfied, and then that means that a certain conclusion was true. So just like the intermediate value theorem, Rolle's theorem also has a set of conditions. In this case, it has three separate conditions. The first condition is that the function is continuous. The second condition is that f is differentiable. Now, these two conditions are actually pretty similar. I've taught you before that differentiability is stronger than continuity. So from your perspective, it should seem a little bit weird why they mention both of these when it seems like you get differentiable for free. The difference between these is the domain. We need it to be continuous on the closed domain, but it only needs to be differentiable on the open domain. In other words, you don't care if it's differentiable at the endpoints. You only need it to be differentiable in the middle. So if you look at this picture right here, this is continuous and it's differentiable in the middle, but the derivative doesn't exist at the endpoints because the function doesn't exist on the right side here and the function doesn't exist on the left side here. So it's only differentiable in between A and B, but it's not differentiable at A or at B. Okay, that's why we have these as separate conditions. The third condition that we need is we need that the y values of the endpoints are the same. So let's take a look at these pictures here. This guy is continuous because I can draw it without lifting my pen off the paper. It's differentiable because there's no discontinuities, there's no corners or cusps, and there's no vertical tangent lines. Those are the three ways the function can fail to be differentiable. Got the same thing here. This is continuous. Oh, and the y values are the same, right? The y values are both equal to each other. This picture as well, it's continuous because I can draw it without lifting my pen off the paper. It's differentiable. There's no corners, kinks, jump discontinuities, or vertical tangent lines. And again, the two y values are the same. This third picture also, it's continuous. There's no jump discontinuities or any discontinuity at all. There's no corners or cusps, and the y values of the two endpoints are the same. So what does the conclusion say? The conclusion says, you know what? There's going to be some points where the tangent line is horizontal. So in this case, there's a horizontal tangent line here. In this case, there's a horizontal tangent line here. And in this case, there's two horizontal tangent lines. There and there. So, one thing you might ask is, why do I care? Why do I care whether there's horizontal tangent lines or not? And the answer to that question is something interesting happens when the derivative is zero. In other words, when the tangent line is horizontal. And the thing that's interesting is that a lot of times you'll have a local maximum or a local minimum. So in these pictures, you can see, oh yeah, the maximum value occurs when the tangent line is zero. The minimum value occurs also when the tangent line is zero. So really knowing when the tangent line is zero is an interesting thing for us. Okay. So I was thinking that we would use this Rolle's theorem and we would do an example together first. So let's take a look at this example. It says, for each of the following functions, verify the conditions the function satisfies the criteria. So we have three criteria. The first criteria is f is continuous on this closed interval from -2 to 0. Now we should all be able to look at this function and immediately tell it's continuous everywhere. So how do I know that f of x is continuous everywhere? That's right. We know it's continuous everywhere since it's a polynomial. So it's really continuous everywhere, including from -2 to 0. What other functions are continuous? Rational functions are continuous, but not everywhere, only on their domains. What else is continuous? Radical functions, roots and radical functions are continuous, but only on their domain. And what else do we have? Trig functions. Trig functions are continuous as well, again, only on their domain. Regardless, the first condition is satisfied. It's over satisfied. Okay. What's the second condition? Second condition is f is differentiable, which I abbreviate as diffable. How do we know that f is differentiable? Well, do you know what the easiest way to show that a function is differentiable is? Differentiable means it has a derivative, right? So what's the easiest way you could show a function has a derivative? That's right. You just calculate the derivative. And if you can do that, then it is differentiable. So let's just calculate the derivative. F prime of x is going to be equal to 2x plus 2. So now we know the derivative exists. The third condition we need to satisfy. Oh, I should have done something at the beginning. I should have specified what the a and the b were. The a is equal to -2, b is equal to 0. Forgot to do that at the beginning. So you always need to specify what your f is, what your a is, what your b is. The third condition says that we need to evaluate f at the endpoints. So if I take f of a, that's going to be equal to f of -2. That's going to give you -2 squared plus 2 times -2. In this case, it's equal to 0. We need to calculate f of b. F of b is f of 0. In this case, that's 0 squared plus 2 times 0. That's equal to 0. So these guys are the same. Okay. Then the conclusion is there exists, this backwards E means there exists. I was supposed to teach you that in the 1.7 section that we haven't done yet. This means there exists. So there exists a C inside my interval from -2 to 0, such that f of c, f prime of c is equal to 0. So in this question, they want me to find these values of c. So how do I find those values of c? What I'm going to do is I'm going to take my derivative, which was 2x plus 2. I'm going to replace the x with a c. I'm going to set that equal to 0. I'm going to solve for c. So this gives me 2c is equal to -2, which gives me c is equal to -1. And a quick check shows you that -1 is inside this interval from -1 to 0. This c is what we were looking for. Why don't you guys try example 2? Okay, you should specify what f is, which is just stated in the problem. You should specify what a is. You should specify what b is. You should show the first three conditions. The three conditions are satisfied, 1, 2, and 3. And then you should also find the c. So I'm going to give you a few moments to try that. So I think the first thing we need to do is we need to identify what f is. So it's written in the problem, but I'm just going to rewrite it for fun. X cubed minus 4x. Our a is going to be -2. Our b is going to be 2. f is continuous on -2 to 2 since it's a polynomial. F is differentiable since I can calculate its derivative, which is going to be 3x squared minus 4. And the third thing is if I take f of -2, I'm going to get -2 cubed minus 4 times -2. That's equal to 0. This is not a good question because with this last question, we got the y values for both 0. In this question, we get the y values are going to be both 0 as well. But we don't need them to be 0. We just need them to be the same. Like I should just come over here and insert like a +1 or something so you don't think it's always 0. Next version of these notes, I should fix that, I think. You plug in a 2, you get the same thing. You get 2 cubed minus 4 times 2. That's also equal to 0. The key point is that these guys are the same. So this means that the mean value theorem is satisfied. In other words, we could say that this implies there exists a C in my interval from -2 to 2 such that f prime of C is equal to 0. I know that this means 3c squared minus 4 is equal to 0 because I simply take my first derivative and I substitute in a C and solve. I get c squared is equal to 4 divided by 3, or C is equal to plus or minus square root of 4 over 3. Is there any questions about this question?